All right, so I was talking about the constellation. I should have just mentioned it before I ran out of time. So the one between Scorpio and Sagittarius is called Ophiuchus. So for about a week or so each year, excuse me, each year the sun is in the constellation Ophiuchus. Although nobody has a zodiac sign called Ophiuchus, even though there's people born when the sun is in that constellation. Again, it's only for a week or so. Um, all right. Anyhow, um, remember when if you think you're a certain constellation, you're not. If you think your sign or whatever is a certain constellation, it's not, because the astrology stuff was established 2,000 years ago, and for some bizarre reason they still use those. They still use those constellations that were in the sky 2,000 years ago, and of course these things have shifted. In you know Anyhow, it doesn't really matter anyway. All right, so you see, of course, you can see the constellations, on the other side of the sun during an eclipse. So this is what I was talking about. So these are called circumpolar stars. The Big Dipper is an example. So here's the 7 stars of the Big Dipper. These 2 stars are called the pointer stars because you follow them and they point to the North Star. And it doesn't matter where the Big Dipper is, right? The Big Dipper does this. It's going counterclockwise around the North Star, and those 2 stars always point right at the Big Dipper. So these circumpolar stars go in circles around the North Star, the pole star, also known as the pole star. It also is called Polaris. Technically, that's the name of the pole star, the Polaris. And so, you can see more and more circumpolar constellations, and the further north that you go. Like, if you're in a northern latitude place, like in Canada or something like that, you're going to see more circumpolar constellations. So because you're closer to where all the stars are going in that, around. Um, those stars are not hitting the horizon, basically. So the further south you are, you're only seeing just a small number of stars that are circumpolar, because the horizon gets in the way. All right, so that's all that is. The one thing to note is, even something like the Big Dipper, the stars themselves are very far away from each other. They happen to be, and some of them are a little brighter than others. So this is just showing you, like, there's the 2 pointer stars, compared to each other. This one's roughly 86 light years away. The LY stands for light years. So the light that you see from this star is 86 years old. That light left this particular star 86 years ago. The light that left this star right here was 62 years ago. All right, and this one right here, it was 116 years ago. Right, that's literally what we mean by a light year. Right. This one right here, the light that reaches your eye from this particular star left that star 360 years ago. All right, so just to let you know, like, the most distant object that you can see in the night sky without binoculars or a telescope is actually the Andromeda galaxy, and it's just kind of you got to know where to look. It's generally observed in the summertime, and it's kind of a hazy patch in the night sky, if you know right where to look. And when you do see that, the light from Andromeda, that light is 2.5 million years old, because that's how far away the Andromeda galaxy is. All right, so that's an entire different galaxy. All these stars and all the stars you see in the night sky, except for the little hazy patch called Andromeda, which happens to be bright enough to be seen by the visible eye, although barely. You can barely see it. But the vast majority of stars that you can see, or I'm sorry, all of the stars you can see, Andromeda is not a single star anyway. But all the stars that you can see are part of our galaxy, the Milky Way. All right, so this is like if you did a time exposure of and you pointed your camera at the North Star. This circumpolar movement of the stars is what you would see, and of course, this is really what happens across the sky. It's just that the horizon gets in the way, and these things will, you usually won't see a complete circle where the stars will dip down below the western horizon and rise up in the western direction, the western horizon, and then they'll rise in the eastern horizon. So you go outside one night at 9 o'clock at night. If you look to the east, you're going to see some stars. Of course, if you wait an hour or 2 hours, the stars that you saw will have moved noticeably to the west. Not a huge amount, but they'll move towards the west, and then stars that were below the eastern horizon have risen up above the eastern horizon. That's just because the Earth's rotating. Right? Knowing the names and constellation tells us much about pretty much the culture of the people that named the constellations. Right. Some of the stars are named after Greek mythology. Some of the stars have names that come from the Arabic world, and like the Chinese had completely different constellations. I mean, it's the same stars, but they had different constellations. So it's B is the anyhow. I'm not sure what was supposed to be right here. This is how this thing appeared to me. Anyhow, I can probably figure it out. Let's see. So a star's color indicates its temperature. All right. So the more red a star is, the colder it is, and that temperature is with stars you have to measure the temperature in Kelvin, which is the absolute scale. Blue stars are a lot hotter than red stars. So when a star is putting out more blue light, it takes more energy to put out blue light than it takes to put out red light. So generally, a bluish star is roughly, this is very rough, roughly twice as hot as a red star. They must be relating the average frequency to the temperature here, something like that. I don't know what the heck they meant to put there. That's not a standard thing. All right, anyhow, which of these stars radiates energy in the longest wavelengths? Just to remind yourselves, red light has a longer wavelength than blue light. All right, so that, of course, would be red stars. That's right. We measure bright stars in two ways. What's called the apparent brightness. So that's just the brightness when you look out at the night sky, and how bright something appears to us. And then there's what's called the luminosity. By the way, the luminosity is also related to a property called the absolute brightness, right? Or the absolute magnitude. Anyhow, we don't have to get too much into the numbers here. The luminosity is always compared to the luminosity of our sun, right? And so the luminosity of the sun, just to let you know, numerically, this is about it's like you say to yourself, hey, I've got a 100-watt light bulb over here. Then you use this thing called the inverse square law. I'll show you that in a little bit, I'll show you a video on that. Anyhow, the luminosity of the sun, the sun's putting out a tremendous amount of energy. it's about 3.9 times 10 to the 26th watts, and watts are units of power. Right, so that's the luminosity of our sun, and we'll compare the luminosity of the sun to the luminosity of other stars. Some stars are much brighter. Some stars are much dimmer than the sun. Right. Let's see. We measure the luminosity as L sub sun. If we were in a spaceship that was twice as far from the sun, its brightness would appear to be, well, see, it's called the inverse square law. So if you're twice as far away, then you have to square, so it's 1 over, 2 squared. So it would be 1/4 as bright or as luminous. Yeah, that's right. All right, so then we get to this thing called the HR diagram. All right, so the HR diagram is plotting the luminosity is along this axis right here. So this is the luminosity of a star versus the temperature, and it's kind of backwards. The higher temperatures are closer to the closer to the left hand side. Normally we have large numbers going to the right, but we actually go smaller when we go this way. Our sun, here's our sun right here. So if you go straight down, sun is right about here. So it's actually a little bit on the other, this isn't drawn very well. It's on the other side of this. They're putting it right at 6,000, which is fine. The surface temperature of our sun is actually about 5,800 Kelvin. So they're saying that a lot of people just round it to 6,000 Kelvin. All right. So notice there's some stars that are much hotter than the sun. There's some stars that are much cooler than the sun. So the HR diagram, also known as the Hertzsprung-Russell diagram, these are the two fellas that came up with this over 100 years ago. It's such an important tool in astronomy. It's kind of like, it's very, and that's what they say right here. This is very similar to like a chemist using the periodic table. Astronomers absolutely need the HR diagram because what it's doing is it shows you stars in different parts of their evolution. All right, so I'm going to spend a little time on this. All right, so this line right here, this diagonal line, it's not exactly straight, but this thing right here is called the main sequence. What happens is when a star forms, right? When it actually forms, it depends on how much mass it starts with, but where it drops down onto the main sequence, like if it has a lot of mass, it's going to be way up here on the main. So the main sequence is just this line right here. Okay, that's just this line right here. This other stuff we'll talk about in just a minute. So this is the main sequence, and stars that are about the mass of the sun are right here, about twice the mass of the sun are right here, and so forth, right? So it's kind of, showing the masses of the stars. And these stars way down here are much cooler than the sun, right? Like there's a star called Proxima Centauri. It's a red dwarf star. It's way, somewhere on here on the main sequence. Now, the thing about this is, stars that are up here, even though they're much more massive than the sun, and much more luminous than the sun, as you can see right here, these stars don't last very long. They go through their life cycle. And so what's the life cycle of a star? It's basically turning hydrogen. Actually, let's use the technical term, fusing hydrogen into helium. That's a nuclear process. So it's the atoms are actually changing from hydrogen atoms to helium atoms, right? That's not chemistry, right? That's quite different than chemistry. In chemistry, the atoms that you start with are still the same atoms that you ended with, but they are now